Hello, my name is Neda Fetch and I'm from the Sabancı University. Today I'm going to present our work on hybrid LiDAR camera fusion for self-supervised odometry. This research is a collaboration between the Sabancı University and Ford Otosan. Autonomous vehicles require continuous localization within the environment. To achieve this, we equip vehicles with a sensor such as camera, and using the sensor data estimate change in vehicle's position and orientation, referred to as odometry. Accurate pose estimation is an important subsystem in localization mapping and a prerequisite for motion planning and control. Even though cameras provide rich information, they fail in environments with low lighting and lack of texture. Besides, cameras provide only 2D features that result in the up-to-scale pose. To achieve reliable environmental perception in all circumstances, it is necessary to add complementary sensors to the vehicle, such as LiDAR. LiDAR provides direct 3D information and very accurate measurements regardless of the lighting conditions. However, obtained measurements are sparse that causes inaccurate 3D correspondences and drift in the pose estimation. In this work, we aim to develop a robust odometry framework that fuses two complementary sensors and enables the vehicle to autonomously drive anytime, anywhere, and under any condition. Existing classical visual odometry approaches, due to the nature of the features, do not generalize well. On the other hand, learning-based methods use neural networks for pose estimation that act as a place recognition algorithms. Existing LiDAR odometry approaches fail when the structure is symmetric or they do not fully utilize geometric constraints. There has been prior work on fusing visual LiDAR measurements. However, most of them are loosely coupled. They do not consider the correlation between the measurements that limits their accuracy. Instead, we present a hybrid visual LiDAR odometry that tightly fuses complementary sensors in a hybrid framework. To the best of our knowledge, this is the first hybrid visual LiDAR odometry method. It consists of an effective sparse-to-dense LiDAR transformation method and a tightly coupled visual LiDAR fusion algorithm. In H-VLO, two image frames are fed to an image data representation module that contains two networks, FlowNet and DepthNet. The FlowNet takes two frames and predicts forward and backward optical flows. The network architecture and loss function are inspired by LightFlowNet, an unsupervised optical flow estimation network trained on a synthetic dataset. Similar to the FVO, we use least forward-backward flow inconsistency to estimate correspondence matches. The camera image is also fed to DepthNet, which predicts depth. It is a stereo-trained unsupervised network with a similar architecture to MonoDep2, but adjusted for online adaptation. The estimated DepthNet map is fed to the fusion module. To fuse depth map from camera and LiDAR data, it is necessary to align their measurements. For that, we first convert LiDAR point cloud to the LiDAR images using the LiDAR camera transformation. Obtained image is sparse and irregularly spaced that represents a challenge for LiDAR camera fusion. To overcome this, we densify LiDAR image using deep completion network. This network is inspired by SSDC, a self-supervised depth completion framework. Obtained DepthNet map and densified LiDAR map are fed to the fusion module. In the fusion module, we first compute confidence maps using negative exponential of their reprojection error. In this way, larger reprojection error is mapped to smaller confidence values and vice versa. To produce high-quality fused depth map, we merge these proposals by utilizing a Bayesian inference module. The proposed fusion map method is fast, produces an enhanced depth, and serves as a real-time domain adaptation of DepthNet. Obtained correspondences of fused depth map are fed to pose estimation module. In pose estimation module, 2D filtered sparse correspondences are utilized in epipolar geometry to estimate essential metrics. The translation recovered from the essential metrics is up to scale. To resolve this, we use 2D to 2D correspondences and compute triangulated depth. Scale factor S is then predicted by aligning triangulated depth values with the fused depth map, resulting in a scale-consistent pose estimates. In the cases when there is no sufficient parallax or motion of the camera is pure rotation, pose estimation from an essential matrix fails. In these cases, 3D to 2D correspondences are used. These correspondences are obtained from the fused depth map and 2D to 2D sparse correspondences. Pose estimation is then recovered using a PMP algorithm by minimizing the reprojection error. To investigate effectiveness of our LiDAR camera fusion approach, we generate variants of our algorithm and observe the effect on the translational error in the KT dataset. Translational errors are averaged on subsequences of sequence 9 and 10. From the results, we observe that the fusion algorithm effectively utilizes both sensor measurements and performs the best among all the variants. Effectiveness of our fusion method is also apparent in the fused depth map. For example, attachments to the roof of the vehicle exist in the fused map where DepthNet is not able to estimate it. Also, when DepthNet is full due to the graphics at the side of the van, our method produces more noticeable vehicle boundaries. Furthermore, we compare our method to the state-of-the-art algorithms from the literature on all sequences. Following other works in the literature, we use average translational error and average rotation error as a performance metrics. We consider a classical VO algorithm ORB-SLAM2, supervised and unsupervised visual and LiDAR odometry methods, hybrid visual odometry, and learning-based visual LiDAR odometry framework H-VLO. The quantitative results show that H-VLO significantly reduces drift and decreases translation error. For the sequence 10, we see a decrease of 39% compared to the best hybrid visual odometry approach. While compared to the state-of-the-art LiDAR odometry approach, we observe a 30% decrease in the translational error. However, no substantial reduction in rotational error is observed. That is because improved scale recovery does not affect the rotation, which is scale invariant. Putting it all together, here is the sequence of outputs for our H-VLO framework on sequence 10. In summary, our framework utilizes learning-based optical flow and depth map estimation from the camera, learning-based parse-dense LiDAR transformation, Bayesian fusion of depth maps, and a geometry-based pose estimation. The framework is a self-supervised hybrid odometry, and as we can see from the trajectory, the drift in the pose estimation is small. In conclusion, we present H-VLO, a self-supervised hybrid visual LiDAR odometry framework. It represents a step toward a more efficient, robust, and accurate localization in all environments. We demonstrate that proposed method introduces improvements in the pose estimation. In the future research, we plan to integrate backend optimization module and automatic filtering of dynamic objects. Thank you very much for the attention. If you have any questions, feel free to reach out to us using our contact details below.